Terrific. All right, well, we'll get started. My name's Mike Schneider. I'm with a company called Hivebrain Software. I'm an independent iPhone developer, and this talk is called Teaching an iPhone to See, Adventures in Computer Vision. And so we're going to talk about a variety of things today, but it focuses primarily on computer vision, object detection, and machine learning. And so to start out, we'll talk about the HAR wavelet mother function, which can be described as follows. That's a joke. The thing about machine learning is it can be extremely complicated. There's a lot of detailed algorithms that are mathematically intensive, but you don't really need to know how they all work in order to take advantage of them. And so this talk is more of a, it does have quite a bit of technical bits and pieces in it, and I do have some code that I'm going to share with you. But the perspective of this is really more of a look at computer vision and machine learning from the perspective of an indie developer who really isn't a computer scientist. I'm self-taught. I used to be a lawyer for many years doing technology law, and I started doing iPhone development when the SDK came out a bunch of years ago. And I just happened to have good timing and had some successful apps, and I was able to leave my big law firm and go make apps for a living. And so I still do that today. But the point of that is that this is about how to do computer vision on the phone, really from a perspective of a guy who isn't a computer science PhD. Hopefully that'll help maybe make it relatable to people that aren't at that level. If you are an expert in computer vision or machine learning, you may not learn a lot from this talk. But my hope is to show you what's possible and help you realize that some of this stuff is not as hard as it might seem, and show you kind of how I did it, so you can learn from that and maybe find some problems that you can solve with the same tools. So for background purposes, computer vision, and this is kind of a complicated, like a precise definition of computer vision. I wanted to make sure I include some of these things because, like I said, I'm not a computer scientist by trade, so sometimes my definitions of things are a little bit loose. So this is the firm, true definition of computer vision. From my perspective, when I think about computer vision, the way I think of it is it's how you get a computer program to understand an image, and that means either an image coming from the camera or from a live video stream, but taking those raw pixels, which are just numerical values for the brightness of each pixel in the image, and turning that into something that the computer can actually do something with that makes sense, and that you can use for decision making or machine learning. Machine learning is another definition I have up here. This is a type of artificial intelligence that provides computers with the ability to learn without being explicitly programmed, and that's pretty exciting because it means you can teach a computer to do something that you may not have previously been able to do if you had to program every bit of the code and the logic by hand. And so object detection is a great example. If you're trying to detect a particular thing in an image, imagine trying to write a program from scratch that actually uses I don't know, whatever logic you can come up with to try to say how to find that. You'd say, okay, well, I'm looking for. You'd have to really break the program down into a lot of little pieces, and then it probably would break pretty easily because as soon as the data that it sees doesn't match up with what your idea of the object is, your program kind of breaks. And so this stuff is super powerful because it allows you to create a program that allows the program to get smarter over time, and to some extent get smarter than you could even get, or your user could get. And so even though this talk is about computer vision, and that because that's the application that I applied it to, I want to take the opportunity to kind of inspire you to think about machine learning generally as an area that you can focus your energy on as an independent developer. It's good for so many things. It's like you'll notice for things like AR applications like the Pokemon Go app that's so popular right now. Object detection in images. Snapchat has an app that does like a live mask over your face. I don't know if anybody's played with that. You kind of tap on your face. It does a face detection to kind of determine where the features of your face are, and then it applies like a live mask over it so that you can look like somebody else or you can look like an animal. Those are all kind of applications of this type of object detection, machine learning, computer vision in app form. But it's also good for a bunch of other kind of enterprise applications, anything that where you're any business or individual who is in a situation where they need to make predictions about things in the future based on a set of inputs that they have at the time can be kind of solved with this machine learning stuff. And so it got me really excited. I was talking with a friend of mine who is working on a machine learning project, and he got me kind of pumped up on it. And I started reading about it and looking at it. And the reason why I was so excited about this stuff is one, it's super powerful. You can solve problems that 5 years ago were not solvable. It's challenging. When I first started doing iPhone apps, the SDK was new, and building an app that did basic stuff was really exciting because I felt like I was doing something that hadn't been done before, and there were a lot of apps that just hadn't been made before. And I feel like that's the type of challenge that I feel like this machine learning stuff presents to me now. Is I've kind of got a lot of the iPhone development stuff under my belt, and this machine learning is a way to kind of take it to the next level and make apps that are more sophisticated, that solve more interesting problems. Another thing is that it's relatively untapped. There are so many problems that can be solved with computer vision and machine learning, and only the really big ones. I would say like the low-hanging fruit is what these big companies are going after. Things like self-driving cars, and I guess low-hanging fruit's not really the best descriptor of that, because it's not like self-driving cars are an easy problem. It's more about them being the most attractive targets. There are huge benefits to be gained from things like self-driving cars, and so all the energy goes toward that. The energy gets put into things like making advertisements that are more effective in selling you things. But there's lots of smaller problems that this stuff can solve, that guys like you and me, or gals like you and me, can all solve on our own, that the big guys are not even trying. Things like, so imagine if you're like any kind of predictive situation. Let's say you run like a bakery or a coffee shop, and you need to know how many scones to buy every day, so that you don't end up with too few scones and people come in and they don't have anything to buy, but so you don't buy too many scones so that they go bad and you throw them out every day. You're trying to predict how many scones to buy. Or if you run a restaurant or like a retail store, and you need to know how many of your salespeople do you need to have on the floor in a given day. You're kind of trying to predict what the traffic's going to be like, and make sure you have enough people to staff it, but not too many people, so that you're spending money you don't need to spend. Those types of examples exist in almost every business, and they're, in my opinion, they're just too small for these big guys to go after. But they represent great opportunities for independent developers to create applications for all these businesses. And then the other thing that really excites me about this is, as an opportunity for entrepreneurship, is that the talent in this area is somewhat underrepresented. The big guys like Google and Apple and Facebook are sucking up all this machine learning talent that comes right out of the universities. And so the people who are classically trained are getting snapped up really quickly. They go to work for salaries, but it means that the marketplace for sort of entrepreneurship and smaller ideas is pretty wide open, because everyone's getting sucked up into these other big problems that are paying a lot of money. So I guess that's good for multiple reasons. In my case, I like it because it means there's so many opportunities that aren't being addressed, and there aren't a lot of people that know how to do it. But for generally speaking, it also makes you attractive to those big companies to get hired if you're interested in that type of job. So it's really exciting. So I started reading about machine learning. There's a Stanford University professor that has a class on Coursera that goes through all the kind of in-depth, low-level stuff. And you know how when you're reading a programming book and you're trying to learn a new skill, and you're reading about it and you're watching videos about it, and then at some point you need to find a project to apply the stuff you're reading, or you just can't really learn it. You kind of, there's a limit to how much you can learn without actually doing. And so I had this thing, and I like to think of machine learning as like a golden hammer. And this is a Sunbreaker Titan from the game Destiny. And so Sunbreaker Titan is the player that I like to play when I play Destiny, and he's got this giant flaming hammer. And so when he activates his super, his hammer lights on fire, and he can throw it at just about anything, and it blows up, and in a good way. Like it causes the desired effect. And so to me, this machine learning stuff, as I was watching these videos and learning about this stuff, I felt like I had a golden hammer in my hand, and I wanted to hit all the things like an angry guy. So I have this hammer. It's kind of like they say, if for the man who only has a hammer, everything looks like a nail. It's also sort of like for a guy who has a brand new hammer that he really loves, everything looks like a nail. And I was just trying to find the thing that I could hit. And so my nail turned out to be object detection for this game Counter Strike. And the way it evolved was, I live out on Bainbridge Island, which is right off of Seattle. It's a short ferry ride from downtown Seattle. And a friend of mine on Bainbridge is also a tech guy, and he's working on a startup that does a thing where he created a hardware that's a haptic feedback device. that originally it went around your head, and it's kind of evolved a bit, and now it works on your neck. But the goal of this hardware was that it has motors around your head, and they vibrate in different spots to tell you directionally things that are happening. And it's meant as an extra channel of input into your brain, so that people like fighter pilots or people riding bicycles could get notified if somebody was coming up behind them. And one of the applications that they've looked at as the big consumer-facing application is selling these types of units to people who want to get better at playing video games competitively. So you wear the headset or the neck unit, and if somebody in a game is coming up behind you and is about to stab you in the back, it buzzes so you know to turn around and try to shoot them. And so they built an application using the haptic headset based on an open source program called Xenotic. And Xenotic is like a first-person shooter, kind of like Counter Strike, but it's open source, so they could get into it and they could write code that would make the game talk to the headset. And they put it on people, and they tested it out, and they found that people were playing the game much better with the headset than without. So that was pretty exciting. Like, the people wearing the headset were winning more than the people without the headset. So that's great news. But the problem is, in order to kind of achieve that result, most games are not open source. The games people play are not open source. You need to go to the game developers, and you need to convince them to integrate your SDK. They built like a Unity plugin that people could use. So it was all set up, but it still requires an awful lot of effort to try to convince every game maker that makes something that you want to work with to adopt your stuff and to incorporate your stuff into their code. I mean, as a developer, it's a tough sell for somebody to convince me to put their third-party library into my app. There better be some pretty big advantages before I start incorporating other people's stuff into my code. And this one is a harder sell, because the thing is, game developers have different motivations than game players. Game developers like their games to be very balanced and fair. They want people to play on an even footing, and players are looking for every advantage that they can get. So me and my friend, we got together. I would like to talk about each other's businesses and try to give each other advice. And I had machine learning on the brain, and I said, why don't you do a thing where you point a camera, like an iPhone app or a mobile app, point it at the screen, and try to pull the information that you need off of the screen and convert that into something that could be used with the haptic headset. You wouldn't have to talk to the developers. You could go straight to the players. The whole thing would happen off of the computer, so technically it couldn't be detected by the game developers if they wanted to try to stop it. He's kind of he's a very technical guy, and he's been kind of interested in machine learning too. And so he was interested, and I was interested, and we kind of decided, hey, let's give it a try. So his company's funded, fortunately, so he was able to hire me for 3 weeks to just give it a try as a proof of concept, to see if we could make this thing work. So I started working on it, so this is what Counter Strike looks like. Counter Strike was the game they decided to focus on first because it's got a massive audience, and it's been around for a really long time, and it's probably not going anywhere. People have been playing Counter Strike for like I don't know 10 years longer. So it's not like they're going to stop in 2 years when and the thing won't be worthless. So we focused on that. This is kind of what it looks like. Let me see if I can get it to play. First-person shooter. You run around. There's a radar in the upper left corner that will show you kind of where you are on the map. And when enemies show up, they show up as little red diamonds. And you'll see that kind of in a subsequent slide. So to get started, he said, hey, why don't you try to do this? So I'm not a computer vision guy. I'm technically not a machine learning guy, other than the fact that I'm really interested in it and I've been reading about it. And so I had to kind of look at what's available to me as a way to solve this problem. And there's lots of different frameworks and libraries you can use for machine learning. You certainly don't want to be in a position where you're writing your own machine learning code. So first thing, I looked at the iOS SDK, because the SDK has some facial recognition APIs in it. There's some things baked in that relate to this stuff. But when I looked at it, it was limited, at least at this time, to detection of eyes, detection of faces, detection of smiles. And I think it was all code that Apple wrote for their camera application, that they just said, oh, why don't we make this stuff available to everyone? So the good news is it's all there. It's accessible. If you need to detect a face, you're in great shape. But if you want to do your own model to detect something else, it really doesn't extend to that, at least not yet. TensorFlow is Google's library that they use for this stuff, and it's not computer vision specific. It actually focuses more on kind of like a deep learning model, which is super interesting. TensorFlow would have been a good way to go, except that TensorFlow, at least at the time, really wasn't running great on an iPhone. They didn't have a iPhone implementation of it, so it would have required quite a bit of work. Caffe is another well-known library that's used for deep learning and machine learning, and it would have been a good choice too. That one is a cross-platform, and it's on iOS, and that would have been a good choice. But I ended up going with OpenCV because I had a little bit of experience with OpenCV in the past. And OpenCV is an open source computer vision library that is really robust. They've got tons of image manipulation functions and methods, and they've also got even though it's a computer vision library, there's a whole module of OpenCV that's just focused on machine learning. So it has a ton of options, and so that's the direction we decided to go. And so OpenCV.org, if you want to find out more about how it works, you can import it into your project really easily using CocoaPods. I also I have a GitHub project that I'm going to share with you in a bit that has it all baked in already if you want to give it a try. But so now you've decided you want to use OpenCV. Then you get into OpenCV and you realize OpenCV has like 20 different methods for machine learning, and they all exist, and you have to kind of figure out which one is the best fit for your project. And so I'm going to mention some of these different ones because your computer vision project or your problem may need a different solution than what I was doing. Convolutional neural networks are sort of what we think of as kind of like a deep learning approach. You probably have been hearing about it lately in the news when you think about like Google and their AlphaGo program that beat one of the best players in the world at Go. These are kind of neural networks that try to emulate how a human brain works by creating neurons that activate when inputs and weights are evaluated. And so they're kind of a general purpose tool. They're not specific to computer vision, although they apply really well. That would have been a good choice, but it turned out that for a few reasons we ended up going with something different. Convolutional neural networks can take a little bit longer to run and detect than what we ended up going with. Template matching is another method that exists in OpenCV, and that's a way of detecting an object by it's more of think of it more as like a photo or an image detection. It's taking let's say you have a logo that always looks exactly the same, and you want to scan an image for that. It's basically taking almost think of it like a raster image being compared to another raster image pixel by pixel to see how close they match. So it's great if you know exactly what something's going to look like. It's not great if you have objects that vary. And the great thing about the template matching is if your object always looks the same and it doesn't have a lot of variance, if you use template matching, you can set up a model with template matching with one image. You can say this is the template. Search these images as the images come in through the video camera. Search for the existence of this image within that image, and it will flag it if it finds a hit. And you don't have to go through this massive training process. Contour matching is another method that they have in OpenCV that's focused mostly on looking at like curves, I think, in the image. I'm not sure about the precise science of it, but I believe it's about edge detection, finding curves, and then matching the math of one curve against the match of another curve. And we tried that, and it wasn't performing particularly well, partly because the objects we were detecting were really kind of basic. They didn't have complex curves. They were diamonds, so it wasn't a good fit. So what we ended up using was this cascade classifier, which is what you typically see used for facial recognition. It's really great for detecting faces. It's been around for a long time. It runs extremely fast, and it can detect things, and it can be adapted to a lot of stuff. So it seemed like a good fit. And so this is roughly how a cascade classifier works. It's focused primarily on looking for lines and looking for edges and looking for corners in various regions of an image, and it's trying to find ways to separate your images. So you have positive images and negative images, and when you train one of these models, you're giving it a bunch of data. You have to sort a bunch of sample data into things that are the object that you're looking for versus a bunch of pictures that don't have the object you're looking for. And so what it's doing when you run a training session on that data is it's trying to find features in those images that do a good job of separating the positives from the negatives. And then they kind of cascade on each other. So they'll try to find a particular feature, like let's say they're looking at, if you're trying to detect a face, we know that faces all have eyes. And so they'll look for what it, and it doesn't know it's an eye, but it's looking for a particular gradient that appears to be like an eye. And if it finds that, then it keeps going and says, okay, well, there's an eye here. This might very well be a face. Let's keep looking. Is there a nose? Is there another eye? And so they call it a cascading classifier because it fails pretty quickly. If you show it something that's not a face and it doesn't find that first thing, it moves on. And if it thinks if it does find an eye, it'll keep going. And so it runs incredibly fast, fast enough to be doing like thousands of checks, maybe thousands of checks every frame. and each frame you're talking about 30 frames a second. So it has to be pretty quick. And so I'm going to show you this demo. I love talks when, for me, the kinds of talks that I like to see at these shows are things that get me thinking about what I could be doing, things that get me thinking about what my next project might be, and things that send me home with some code I can play with, but don't necessarily try to live code on stage. And so this is a GitHub repository that I set up. It's a very simple demonstration of Cascade Classifier, and it looks a little bit like this if you run it. It's I didn't quite realize the room would be this big, so this is a pretty small iPad. But when you run it, you get a full screen view, and then when you point it at stuff, it should put a little green box around a face if it sees a face. And so what it's doing, and I'll break down kind of the steps that it's taking, but it's running a model that can detect faces, and those models are XML files. So that model was created outside of the application, brought into the application, and then you show the picture to it, and it highlights whether the face is there or not. And so it's kind of like if you think of this machine learning stuff as kind of like a server-side, client-side thing, this is like the client side. You spend a lot of time training a model on a PC or a desktop computer, and then you move that model in a small file, and then it runs on the user's hardware to do the detection. So I'll explain a little bit about what's happening. Let's see if I skipped a. I'm all over the place. Let's see. Okay, so you may not be able to read the code on here. It's relatively small to type. Don't worry about the code itself. I'll just walk you through kind of what the process is. So you bring OpenCV into your project, and then you import it into the file that you're working with. OpenCV is a C++ based language, and so in order to use it with Objective-C, you have to do what they call Objective-C++, which is pretty simple. You basically just change the .m to a .mm in your project, and that tells Xcode that you're trying to combine Objective-C with C++, and that'll allow you to run some C++ type functions. And so you do that. Then you load the classifier. So in that load classifier function that I have set up, it basically is saying, hey, here's the XML file that you should be using. Load that in and get this classifier ready to start detecting stuff. And then I have this method called start camera, which instantiates this video camera object, which is part of OpenCV, and it handles taking all that imagery from the camera. So you initialize that object, and you pass it a reference to an image view in your iPhone application. So you give it this image view, and that image view becomes kind of like the screen for what's happening. So the images will come in for the camera. They get routed through OpenCV, through whatever filters and whatever detection you want to do, and then the resulting image is presented in that image view. And so even though an image view is typically thought of as being like a static image, it'll cycle through the frames as they come in, and it'll show you a moving picture of what's happening. And so you set some parameters like whether you want to use the front camera or the back camera, how big you want the image that's going to be captured, whether you want portrait or landscape orientation, how many frames per second you need, and then whether you want a grayscale image, and then you tell it a delegate, because what it's going to do then is once you start the camera, you say video camera start, it'll pop up and say to the user, hey, are you okay with this application looking at your video camera? The user says yes, and then every frame, this method gets called and passes in the image from that frame. And so everything you need to do this is in that GitHub repository. You've launched it up, and this will pass you frames, and you can start doing whatever you want with those frames, even if it's not this particular thing. And so I keep this in a separate method because sometimes you want to do stuff to that image before you run a Cascade classifier on it. Sometimes you want to filter it or resize it, and so you can do that there. But then eventually you call this code, which is the Cascade classifier being called into effect. The method that we care about here is the one that says detect multiscale. That's that classifier that you created using that XML file. You say detect multiscale. You pass it the image that came in from the camera, and then there's some parameters that you set that I'll talk about a little later. And what happens is you start getting back every frame. You get a array that's stored in that face rex object that gives you an array of all the hits that it finds. And so if that array is empty, it didn't find a face, or it didn't find the object you're looking for. If that array has 5 rectangles in it, then those are the locations within that image that the thing it was looking for were found. And so anything you want to do with those rectangles, you can put them in a for loop, and you can do what you like. And that bottom line there is basically just OpenCV drawing a rectangle around the thing that it found. And that's just optics. Everything else that you want to do with that data is up to you. You can put, in my case, it was take that data, try to figure out, okay, here's the box. The box is what's the relative position, and send that out to the headset. But anyway, so this is a general purpose detection that you can use for any of your applications once you make an object model that can detect the thing you're looking for. So let's see. This is an example of the radar that I was looking at, and you'll see you got these little diamonds that are running around. Sometimes they turn to question marks. Sometimes they turn to triangles. There's these little orange or these little yellow circles that we have to make sure we don't accidentally flag. And so the question was, how do you get started training this model? And Cascade Classifier, as I mentioned before, it works in the way a lot of these machine learning type algorithms work. Is you have to pass it a lot of data. So you have to give it data and then tell it whether that data is a positive example or a negative example. And so I started by taking pictures of the radar with the camera on my phone, and then cropping them and creating about 100 positive samples, and then probably 300 or so negative samples. And the negative samples are super easy, because a negative sample can be anything that isn't a triangle or isn't a diamond or the thing you're looking for. So you can take any kind of image and just chop it up into a bunch of pieces, and you got a bunch of negative images. And so I did that. And so the result was pretty terrible, because it's only 100 samples. It looked a little bit like this, and it's just kind of all over the place. It's detecting all kinds of random noise. Sometimes it gets a diamond, sometimes it gets a triangle. But it's kind of trying really hard, but it just isn't smart enough to know what it's doing. That's one of the things you'll learn. Machine learning feels like this giant golden hammer, and it's going to solve all your problems. And then when you start using it, you start to realize machine learning is like super dumb. It only knows exactly what you tell it, and it was supposed to just learn this stuff. But you have to really, in practice, it tends to not actually be as easy as you'd think. There tends to be a lot of thought in between every stage to try to figure out how can I make this thing work better. And so I had done this. I think I added some more samples, and it still wasn't performing amazingly. And so at that point, I started thinking, well, there's two things I did. One is I need to start capturing the data that it's capturing, all the bad hits. So every time it thinks it found something right, I want to write that to a file. So after I run it and see that it's terrible and doesn't work, at least at the end of that, I have a whole folder full of examples of things that actually thought were supposed to be good, and then I can sort those. And that turns out to kind of accelerate the process, because you're looking at what the computer got wrong and then correcting it. And so that's great, and you do that in kind of iterations. And every time you do it, then this folder you have full of samples, which kind of look a little like this. This is these are some negative samples, some positive samples. You end up with thousands of samples in a folder on in your Finder here, and literally just taking one folder in the middle, directories on the side, and just kind of dragging groups of images into the one that they belong in, and then running it again. And it gets smarter that way, but it wasn't getting smarter fast enough. And it occurred to me that it was picking up a lot of things that really weren't like those little orange circles would sometimes feel a little bit like a diamond, because diamonds and circles, when you kind of get to be a small image, sometimes the edges aren't that clear. And so it made sense. I thought, well, I should really think about filtering out everything that isn't red, so that I'm not giving the computer so much noise to deal with. And so luckily, OpenCV has tons of image processing tools. And one of them is that you can take any image and you can split it out into its various channels, and then do some math on those, and then turn that into a new image. And so this is a method that's in that GitHub repository that you can play around with. It will take the image that comes in from the camera, and it will what it's doing is, at first I thought, hey, let's just look at the red channel, and make that red channel the thing we look at. Problem is that white has a really high red count. So all of a sudden things that are white are going to start. The computer's going to think anything that's got white in it is red, or things that are not entirely red. They have a lot of red in it, but they also have a lot of blue. All of a sudden, that's a purple, but it's showing up as 100% red. And so what I ended up doing was taking the red value and subtracting some percentage of the blue and the green, so that I would filter out anything that had red, blue, and green, and try to only show things that are truly, only red. And that I'm trying to think if I can, probably won't work very well on here, but this filter's in the GitHub repo, so give it a try. If you turn it on, you'll notice that whatever you point the camera on, the screen's going to look all black except for red stuff, which is going to look white. And one of the reasons this is important, I guess I forgot to mention, all these algorithms have upsides and downsides. And one of the downsides of this cascade classifier method in OpenCV is that it only works with grayscale images. And I don't know if that's just because it runs faster that way, or if because faces are not a thing that this thing was developed for faces primarily, and faces are, detecting a face doesn't really rely that much on color, and things like detecting what a car looks like or a bicycle. All those colors can be totally different, and it might still be a bicycle or a car. But in this case, we really only did care about the red, so I had to create a grayscale image that was more relevant to the system, and this is the method I did to do it. There's also things like detecting edges in images is extremely easy in OpenCV. In 4 lines of code, you can take that input from the camera, and you can do like, have you ever done like a Photoshop filter where it does edge detection, and all of a sudden it's only showing you the edges of the image? It does that really fast and really easily, and you can detect those edges before you do your detection. We tried that; it didn't really help in this particular case, but in another instance where maybe color isn't as important, but the edges are more important, this might be a good way to improve the detection. And so I'll show you kind of where we went. This is probably 2,000 or 3,000 positive images, and color filtering, and it's starting to work. Like, it's still getting some bad hits. Diamonds the yellow triangles lighting up, but it's starting to work. And one of the things about machine learning is that as you're training one of these algorithms, or you're training a model, it tends to like improve quickly and then kind of taper off. So toward the end, it gets harder and harder to get these improvements. But eventually, it ended up taking around 20,000 positive images and around the same number of negative images to get to this point where it really was running perfectly well enough that it was giving the users exactly the data that they needed. And so that was pretty exciting. And so, mission accomplished. And we did that in 3 weeks without having any real prior machine learning experience. So I guess the point is this stuff is accessible. It's something that anybody can do, even if they're not a super sophisticated computer scientist, and it's fun. And we learned some things that I tried to think about what I can convey to you if you guys ever try to do this that you might not know going into it. And one of the things is that the image size is a big deal. We ended up doing like about a 32 by 32 image for the samples that we ran through the training. And the reason is that the bigger the images that you're trying to train on, the longer the training takes. And so to do a 32 by 32 image with like maybe a couple hundred samples is going to take you maybe 10 minutes. But once you get up to like 20,000 samples, that same detection ends up taking maybe like a day, like 24 hours. And if you go to 48 pixels, now you're looking at like several days. And then if you go to 64 pixels, you're looking at like more than a week. And a lot of the training we did on this next thing I'm going to show you, did take it took a week every cycle. The computer just had to think for a week to figure out what the best choice of these classifiers was to differentiate. And so just to give you a sense, when you're trying to think about whether this particular solution might work for your problem, the images that you're trying to, or the object that you're trying to detect within an image needs to be somewhat distinguishable at 32 by 32 pixels, or maybe a maximum of 64 by 64 pixels. Otherwise, it's going, unless you have a lot of time, you're going to have to let the computer run for quite a long time. So let's see. Was there anything else? There were some other things that we learned. Grayscale, filtering color. There's a lot of tinkering that goes on. I kind of the subtleties of how you train these models is a little bit more than I can get into in this talk. But there's a lot of parameters that you pass into the model in terms of how quickly should it assume that the classifier that it found is good. What's your acceptable error rate? And how many stages do you want it to run before it stops? And those are things that you kind of have to just play with and see what works. And I have a feeling it just varies from project to project. And it's one of those interesting things about this machine learning stuff, that it's unlike a lot of programming that you'd probably do. There isn't like a go-to answer for a lot of this stuff. A lot of it needs to just be played with and experimented with to see what gives the best results, which actually makes it kind of fun. because you get to think, hey, what can I do to make this better? You get to implement it. It doesn't work, and you're disappointed. And you get to think of another solution, and it does work, and then you feel great. So the second one we did was a lot easier. And I don't know if you recognize this game. This is a game called League of Legends, which is also very popular. Probably not going anywhere anytime soon. And in League of Legends, there's this little mini map at the bottom of the screen that you sort of see down there, and the mini map shows where your enemies are. And so we tried to work on the same process for that. Luckily, it was also red, so I got to use my same red filter that I used. And we were looking for enemies that have these red circles around them. And it was a little complicated because sometimes the red circles overlap. The red circles all have different stuff inside of them. Every character has a different middle. And so this is what it looked like when we sort of ran it the first time. Similar sort of all over the place stuff. Occasionally getting it right. And we iterated through that, and it got a little better. Starting to see, but it's still pretty terrible. And it ended up being about the same thing, about 20,000 images were what was necessary. 20,000 positive samples were what's necessary to get it to work. This is almost working. You'll see it's like really flagging the thing that needs to flag, but occasionally getting a bad one up in the corner. One of the tricky things about this is Counter Strike. There aren't a whole lot of red things in the radar, but in this, there's tons of other red things that appear on the maps, including things that are like in the middle of the circles. And then this is the one that we did that eventually worked great, and now is part of the product. And it's I don't know if it's showing, but it'll track all the bad guys. And what's great about this particular application is apparently in League of Legends, people go hide in the bushes, and so they go off the map. And people that are playing the game don't know where the bad guy is and where he's waiting to they call it ganking you. And so they're saying it's like anti-gank protection, that when a new character shows up on the screen that previously wasn't there, it notifies you to say, hey, there's somebody new. You should probably take a look at the minimap and see where this person just showed up to make sure they're not about to surprise you. So I mean, that was kind of the talk went faster than I thought it would, but I can do questions. The main thing that I wanted to leave you with was, I hope this stuff is can give you sort of an example of some things you can do and give you some inspiration to find projects where you can either apply computer vision and object detection or machine learning generally. This stuff is super exciting. It gets me excited in the same way that iPhone development got me excited when the SDK came out. And that's not to say iPhone development doesn't still get me really excited. But do you remember, if any of you guys were developing when the SDK first came out, there was this moment when it was like, hey, I've got the ability to make an app. And everybody wants an app, and not a lot of people know how to make apps. And it's like you just feel like you're in the right place to implement these skills. And everything you look at starts to look like an app because there's so many apps that haven't been made yet. Now, I still love making apps, and it's great. But it doesn't feel like there's so many more apps left to be made. You have to think awfully hard to think of an app that isn't already out there. With machine learning and this computer vision stuff, there are applications everywhere that haven't even been considered. And the stuff with like drones and like all the robotic stuff that's coming down is all going to need really great computer vision work. And so it's super applicable, and it just feels really exciting in the same way that the SDK felt at the time. And since you guys know how to make mobile apps, if you guys can just learn how to do a little bit of machine learning, you can make a class of apps that are inaccessible to all the sweatshop developers that are making apps cheap. You can make a different class of apps than them. You can do things that they won't be capable of. And there are tons of opportunities. The other thing about it is that the stuff is accessible. There's tons of documentation online. The frameworks exist, so you can stand on the shoulders of these people who have written these amazing libraries. The advances that are happening in machine learning, I don't know if this is, I'm not, like I said, I'm not a computer scientist, so I don't know how typical this is, but every week or so, there's another paper that comes out of another group, either Google or some university, announcing some advance they've made in their machine learning algorithms, particularly around deep learning and I think they call it deep Q learning, which is what they use to train the computer to beat AlphaGo. I mean, computers can do stuff that humans aren't capable of doing, and the way to do that is being published weekly, where you can find it and look at the algorithms they use and implement them yourself. And it's not that inaccessible. So you can do some like really truly cutting edge stuff, and you can move on it so much faster than a big company can. In the same way that we could move on things faster when the SDK came out. So I guess my takeaway here is start looking for nails that you can hit with this giant flaming golden hammer, and grab the demo and play with it. See if you can train a classifier and make it work. And thanks for your time. It's been great. We still have some time. If anybody has questions, happy to answer them, or take a break because I know that we started a little late. So, yeah. How much work? So the great thing is the sample images don't go on the iPhone. The sample images happen on the desktop to create this XML file. So you feed all these sample images in, and then it gets reflected in an XML file that's only like a couple K. So you're dropping this XML file that's this tiny. It's basically like the essence of what it means to be whatever it is, a face or a bicycle. Even if you have, well, you need to have relatively small images to do the training. So it needs to be able to, if you take the big image and you shrink it down and you can still tell what it is, it'll work. But what the Cascade, there are a lot of things I wanted to talk about in the talk that I just skimmed over, but the Cascade classifier detects at a bunch of different sizes. So you give it a massive image, and it starts with a tiny little rectangle, and it scans across, and then it makes the rectangle bigger, and it scans across, and it makes it bigger. So it can detect that image whether it's tiny or big, and you can tell it how tiny or how big. It helps to, it's super powerful stuff, and it runs so fast. Yeah.